Domain for a graph runs along the x-axis from left to right. When determining the domain of a graph, look for holes that aren't plugged by closed dots that are on the same vertical line, gaps, or vertical asymptotes. A vertical asymptote is when a graph looks like it points straight up or down. You would have to pick up your pencil to continue drawing it. Sometimes I will plot the vertical asymptote for you, and other times it will be implied. You just have to pay attention to what's happening to the graph. When we write our domain for graphs, most of the time I want you to write an interval notation. You will use parentheses if you have a hole, if you have a vertical asymptote, anytime you have infinity, which would be arrows on your endpoints left and right, and if you have an open circle. The only time you're going to use brackets for domain is if you see a closed dot on the endpoint specifically. So let's talk about domain. Let's do these 4 examples here for these graphs. This first example here, find the domain. So from left to right, this is the x-axis. I'm going from the negative side of the x-axis to the positive infinity side of the x-axis. All you have to do is say, okay, the left-hand side has an arrow, so that's the negative infinity side. So there's an arrow on the negative infinity side. The right-hand side also has an arrow on the positive infinity side. There weren't any holes, vertical asymptotes, or gaps. So this domain's kind of boring. It's just negative infinity to positive infinity. Let me change that slightly and give you a slightly different example now. Okay, now what? Let's do our domain for this graph. All right, again, I don't have any holes, vertical asymptotes, or gaps, so I just have to go from left to right on this graph. So the left-hand side of my graph, once again, is an arrow on the negative infinity side of the graph. The right-hand side of my graph is this open circle, specifically at x equals 5. It's an open circle, so use a parentheses. The only time you're going to use a bracket is in this next example. Or if you have graphs like this next example. So here's our next example. We don't have any holes, vertical asymptotes, or gaps. So we just need to go from left to right. So the left-hand side of my graph is right here. It is on the negative infinity side, but there's not an arrow there. It's a specific starting point. So I start at -3. The right-hand side of my graph is here. This is the positive infinity side. So that means that it goes to positive infinity. And in interval notation, since this was a closed dot, I need a bracket at the -3. An arrow always uses parentheses because that is infinity. All right, I keep talking about holes and unplugged holes versus just a normal hole. What does that mean? Let's look at this example here. All right, in this example, I have 2 holes here. This one is at x equals -4, and this one is at x equals 1. In this first hole, there's nothing else on this vertical line that would possibly fill it in for us, so it matters. That means I'm going from left to right. From the left-hand side of my graph, this is the negative infinity side, has an arrow. So from negative infinity all the way until I get to this hole is the first part of the domain, and then that hole breaks it up. And I have a second part of the domain on the other side of the hole, so it stops at -4 but picks back up immediately on the other side. And I keep going. Oh, there's another hole here. But in this same vertical line, there is this closed-in dot. So I can think of it as a plug that's going to plug in this hole. So for the sake of domain, I can just pretend the hole doesn't even exist and just pretend this is one nice, smooth, continuous graph. So from -4, there aren't any holes, there aren't any vertical asymptotes, there aren't any gaps, and it ends here at an arrow on the positive infinity side of the graph. It doesn't matter the arrow is pointing down because that would refer to a y value up and down. I'm going left to right. So it's on the right-hand side, pointing slightly towards the right to positive infinity. This is my domain. All right, and what about asymptotes? So a vertical asymptote, I will try to remember to draw it in for you, but I may not remember to draw it in, so you just need to pay attention. Does the graph look like it's pointing straight up and down on some vertical line somewhere in the graph? And in order for me to continue drawing this, I had to physically pick up my pencil to come down here to finish this other loop. So I have an asymptote here at -2 that I need to worry about, and then I have another hole here at 1, and on this vertical line there's nothing to fill it in. I don't have another closed dot anywhere there. So my domain is, this is the negative infinity side of the graph, so from negative infinity all the way till I get to the asymptote at -2. On the other side of the vertical asymptote, so from -2 all the way until I get to this hole at 1. And then on the other side of the hole, the rest of the graph to the positive infinity side goes there. Let's do a few more examples. Determine the domain of these 4 graphs. You may want to try and pause the video and figure out the domain yourself and then double check with my work. So for the first graph here, there aren't any holes, there aren't any vertical asymptotes, there aren't any gaps, so I just need to read from left to right. So the left-hand side of my graph here is at -3, the right-hand side is at +2. Use a bracket for the closed end dot and parentheses for everything else in your domain. All right, second graph. I do have a physical gap here, right here. Finally, you get to see what that means. So I am going to have 2 pieces to my domain. I'll have the first part, the first interval deals with this curve here, and the second interval will deal with this curve here. So this first curve from left to right, it goes from -6 to -2. Use a bracket when you have a closed end dot. This second curve or line, the left to right, so it goes from 1 to 3. Use a bracket for the closed end dot only, and a U between them. I took this example from a calculus test that I saw, or something similar to here, so just know that domain will come back up to haunt you if you don't get it now. So here's this graph. We need to figure out what the domain is. I have a lot going on. I have a lot of holes here. I have this hole at -3. Oh, but luckily this dot is plugging it in. I can pretty much pretend that this hole does not exist. I have another 2 holes at x = 1, but again, I have this to plug it in. It doesn't have to be a 1-to-1 correspondence. As long as there is 1 dot, it fills in all the holes in that same vertical line. So again, I can just pretend this is one smooth continuous line for domain purposes and ignore that there was ever a hole. And then finally, I do have another hole at +3. There aren't any dots here to plug it in for me, so this one is going to affect our domain. So domain from left to right, so from not -4. There's an arrow there. This is the negative infinity side of the graph. So from negative infinity all the way until we get to this problem hole at 3. And then you start on the other side of the hole till you get to the positive infinity or arrow side of the graph. And then here in this last example, I did not draw in the vertical asymptote for you. Hopefully it's not too hard to see while I free-handed this really poorly. But hopefully you kind of get the picture. So there's an asymptote here at, that was supposed to be -1, but I guess we'll call that -1.5. I know that's not right either, but whatever. Okay, there's a vertical asymptote here, and there's another hole here at 1, but luckily it is being plugged in by this dot, so I can ignore that it exists. So my domain from the negative infinity side of the graph all the way until my vertical asymptote, and then I'll pick up on the other side of my vertical asymptote and go until that's the positive infinity side of the graph.